Hi there, Dr. Steve Kuchnicki here, and today I'm going to talk to you about parallel axis theorem, giving an idea of how it works, where it came from, and then there will be another video after this where we'll talk about how it's applied. So in this case, we're talking about the derivation, so to speak. So what we have here is a rectangle, height h, base b. We're using the z-axis that I've drawn in here as a reference, and we're saying the moment of inertia about the z-axis, this one passes through the centroid, right? And I'll put a little c here, so we know it's got the centroid that it's passing through. Our coordinate origin is at the centroid, the way we often do in a solid mechanics class, right? And Iz is equal to 1/12 bh cubed. Now, if you think about the definition of that, right, this comes from the equation Iz is equal to the integral of y squared dA over the entire area. Now, when I say that, what I mean, of course, is this is really taking the integral of the distance from that z-axis to every point. So I look at every point in the area, and I say, okay, the distance is so far, the distance is so far. We add them all up, and that distance, of course, is the perpendicular distance, which is going to be defined by the y-coordinate. Okay, great. This all makes sense. We could work that out if we had to, and in a minute we will work out one of these. But what I'm going to do is I'm going to work out a slightly different one. I'm going to use my y1 z1 axes to prove a point and to show how the nuts and bolts of this actually works. Okay, so now I'm going to use the y1 z1 axes. I want the moment of inertia iz1. Okay, well, iz1 is equal to the integral over the area of the distance from the z1 axis. Well, that's going to be y1 now, not y. I'm going to have to square that. I've got to multiply that by dA. Okay, and I've got to take the integral over the whole thing. That's what the little a down there means. Okay, great. Well, what that equals, I can split the dA into a chunk dx going across, dz going across, I'm sorry, and a chunk dy going up. So I could call this a double integral. And if you've taken a Calculus 3 class, or if you've taken some kind of engineering math class at some institutions, well, hey, you can figure out how to handle this integral. You don't need to know it too much for this purpose, but I'm still going to have y1 squared. I'm going to have dy dz. dy is my little vertical chunk. dz is my little horizontal chunk. And in fact, it's y1 and z1, because those are the axes I'm using. And I'm going to go from 0 to h in the y1 direction, and 0 to b. 0 to b, let me erase that and make it a little better. 0 to b in the z1 direction. And my integral sign decided to disappear for a second. Hey, look, there it is, right? And if you know the rules of integration, you know I can write this again as integral 0 to h of y1 squared z1 dy1 evaluated for z1 equal to 0 to b. And we ignore the y1. We don't think of it as a variable. It's not in this case because we're changing around the z's. So this is equal to the integral from 0 to h of b y1 squared dy1 is equal to b y1 cubed over 3 from 0 to h is equal to b h cubed divided by 3. Well, that's not bh cubed divided by 12 now, is it? Right? The axis we're taking the moment of inertia about matters. The smallest moment of inertia is always going to be about an axis through the centroid, and no matter where we look anywhere else, it's just going to get bigger. Now, we could do the integral all the time. We don't want to do the integral all the time, right? There needs to be some fundamental thing we can do to kind of shortcut this process. That's where parallel axis theorem starts to come in, okay? And to show how this works, I'm going to come down here, and I'm going to draw what one of my graduate professors always called a generic blob. It's just a piece of area. And I'm going to put some axes through it. I'm going to call them z prime and y prime. Okay? And I'm also going to put some other axes on here, z and y. I'm going to say that z prime, y prime, that's sitting at our centroid. Okay? Now, what we know is that our moment of inertia about the centroid is going to be equal to iz prime, which we'll call I bar to make it look special because it's through the centroid. And that's going to equal the integral over the area of y prime squared dA. I need one more piece of information to make this go. I need the distance to get from my z-axis to my z prime axis. All right, I need that distance in here. I'm going to call it little d. Okay. What I want is I want the moment of inertia about the z-axis, just like we saw for the rectangle, right? We had the initial axes, y and z through the centroid. We have y1, z1 down at the bottom line here, and we want to know what the moment of inertia about that new axis was. Well, we want to do the same thing here. Okay, so let's remember what we have with I bar. That's a good spot to leave it. Iz is equal to the integral over the area of the distance from the z-axis squared, well, that's y squared, times dA. Okay, that's what this thing actually is. So now, what we have to note is if I have any point in this body, y has to equal y prime plus that distance d. Okay, what's happening here is if I look at any point, if it has a y coordinate of y prime, I have to add on d to get its y coordinate, otherwise known as, let's think of it as having a ½ inch above the z prime axis. If d is 2 inches, it makes sense that the y coordinate would be 2½ inches, where the y prime coordinate would be a ½ inch. So what we can say then is that we can say the integral of y squared dA is equal to the integral over the area of y prime plus d, pardon me, got a little ahead of myself, of y prime plus d squared dA, okay? And that is then equal to the integral over the area, and I'm going to assume that you're going to think, hey, you know, you're making a mess out of this, because we can FOIL this, right? And that's going to make things look worse for a few minutes. But the way a lot of these things work out is they look worse for a few minutes, and then suddenly they look a heck of a lot better. So I'm going to have y prime squared plus 2d y prime plus d squared all times dA. Okay. And math says that I can have this split up into its parts. I can take the y prime squared by itself, multiply by dA, add in, well, I'm not going to even put the 2d inside the integral anymore, right? 2d integral of the area y prime dA plus d squared integral over the area d squared times integral of the area of just dA. I got a little y prime on the brain on that one. Okay, so I've got the integral over the area of y prime squared dA plus 2d integral over the area of y prime dA plus d squared integral of the area of just dA. And if you're in one of my classes, you've seen me take out the purple pen, and usually the purple pen means some stuff's about to go away, and this is no exception, right? Integral y prime squared dA. Hey, wait a minute, I've seen that one before. It's up here. It's Iz prime, or I bar, the moment of inertia about its own centroid. Hey, well, this is what we called I bar. Well, the integral over the area of dA is just the area, right? So this term here is just area times d squared. And now what I have to do is figure out what this thing is. Because if I can figure that out, I've got this whole thing figured out. right? And hopefully it'll be some kind of nice, easy equation to work with. So the integral over the area of y prime dA, you may have seen it before. It actually has an appearance in the centroid equation. And we're going to use that to our advantage, which is why it's important to note that this is true. Okay, so it appears in the centroid equation, right? Remember the definition of the centroid. If I can say y bar prime, right? The centroid location in the y prime axis system, or the y prime direction, is equal to the integral over the area of y prime dA divided by integral over the area of dA. Well, funny thing is, we put our centroid at the origin. That has to equal 0. Because our centroid is at the origin. I'll put the word "the" back in there. Of that y prime, z prime coordinate system. Well, because that's at the centroid, right? The centroid is at the origin, I should say. What that means is that this fraction that I've got here, this little fraction, has got to somehow evaluate out to be 0. Well, the denominator is not infinite. I don't have infinite area. That makes no sense. So all that I'm left with is that the integral over the area of y prime dA is equal to 0. That means this entire center part, the part with the question mark, is gone. This is 0. And that gets us to the parallel axis theorem. Moment of inertia about that parallel axis, here the z-axis, is equal to moment of inertia about its own centroid plus area distance squared. That is the statement, if you will, of the parallel axis theorem. So how can we see that it works? Let's go back to that rectangle. Right? Let's take a dive back into that rectangle. If we look at that rectangle above, right, that means that our moment of inertia about that z1 axis, right, should be equal to moment of inertia about the centroid plus area times the distance that we moved the axis, so to speak, squared. Well, this moment of inertia is our familiar 1/12 bh cubed. This area is base times height. And d, I'll make sure I'm going to note that it's d and not d squared. Well, we moved it half the distance from the centroid to the edge, so it must be just h over 2. So that tells me that IZ1 is equal to 1/12 bh cubed plus base height over 2 squared. I hope you're seeing that we're going to have a bh cubed in both of these terms now, because I've got bh cubed explicitly here, and I've got bh times h squared here. Hey, I've got a bh cubed. So it's 1/12 plus, well, 1/2 squared is still 1/4 bh cubed, and that's 1/12 plus 3/12. That sounds like 4/12 to me. That's a third. 1/3 bh cubed, and that's the same as what we saw above. Okay, so that's how parallel axis theorem comes about. That gets us a nice general statement of it. That is, moment of inertia about a parallel axis is equal to moment of inertia about an axis through the centroid plus area times the distance between the axes squared. Right? I'll have another one up soon that has the same sort of stuff, except we're going to talk about how to use it for specifically the case of an I-beam made of a couple of rectangles. Thanks for watching.